Psychrometrics Lesson 2.2 Air Conditioning Processes and the Psychrometric Chart. The purpose of an air conditioning equipment is to change the condition of the air from some entering condition to a leaving condition. We refer to this change of condition in the air sample as a process. In this sectional view of an air handling unit, there are a number of air conditioning processes that can occur. The outside air enters the unit at an outside air condition and is mixed with the return air from the spaces. Both the outside air and return air will undergo a process change due to the mixing process itself. The mixed air may experience further changes depending on the processes that occur next. It could experience a change in dry bulb temperature due to heating or cooling as it passes over the heating and cooling coils. It may experience a change in moisture content if moisture condenses out, and of course a change in enthalpy depending on the application. In this tutorial, we'll discuss these processes and how they are represented on a psychrometric chart. On a psychrometric chart, a process or change in properties of air can be represented by drawing a line from the entering condition to the leaving condition. The first process that we will look at is sensible heat change. In sensible heating or cooling, heat is added or removed, resulting in a change in the dry bulb temperature. Since moisture is not added or removed, this process follows a line of constant humidity ratio. Sensible heating results in an increase in the dry bulb temperature. Notice also some other changes in properties that will occur. The relative humidity is reduced and the specific volume is increased. In addition, we see the specific enthalpy also increases. Sensible cooling is the process in which the dry bulb temperature is reduced, but without a change in humidity ratio. During the sensible cooling process, the relative humidity increases, the specific enthalpy is reduced, and the specific volume is also reduced. Latent heat change. When water vapor is added or removed from the air, it is referred to as humidification or dehumidification, which results in a latent heat change. In this process, the dry bulb temperature remains constant. The humidity ratio is either increased, as in humidification, or decreased for dehumidification. Because the dry bulb temperature is not affected, there is not a sensible change in the air temperature. Note that in the humidification process, the specific enthalpy of the air is increased, and in dehumidification, the enthalpy decreases. Air can undergo a combination of sensible and latent change during an air conditioning process. The four scenarios that are possible are sensible heating and humidification, sensible heating and dehumidification, sensible cooling and humidification, and sensible cooling and dehumidification. Please note that in general, the dry bulb, wet bulb, and specific enthalpy also change during these processes. For example, in the cooling and dehumidification process, the dry bulb temperature is decreased, the humidity ratio along with the specific enthalpy also decreases. This is due to both sensible and latent heat removal. This is one of the most common and often useful processes in air cooling applications. Sensible change is shown on the psychrometric chart as a process line along constant humidity ratio, as illustrated earlier. The sensible heat equation can be applied to the moist air in the following equation, where Q sensible is equal to the mass of air times 0.24, which is the specific heat of air, and the change in temperature, plus the mass of the water vapor times 0.45, the specific heat of the water vapor, and the change in temperature of the air sample. For air conditioning applications, it is common to see the second term for water vapor neglected, since it is typically too small to be of any significance. And therefore, the sensible heat equation for air is sometimes simply shown as Q is equal to 0.24 times the mass of air times the temperature change. Since air conditioning processes typically involve the flow of air, and because most instruments read the airflow in cubic feet per minute, or CFM, another convenient form of the sensible heat equation is often used. The relationship between mass flow rate in pounds per hour and CFM is shown here. Pounds per hour times 60 minutes per hour times 1 pound per 13.3 cubic feet of air. This is the specific volume of air at certain conditions. Typically, we use this condition as standard air, which is at 68 degrees Fahrenheit and 29.92 inches of mercury. We will often hear this referred to as standard air condition. And now, substituting into the sensible heat equation, we arrive at the familiar and very useful equation for sensible change of air as Q sub S is equal to 1.08 times CFM times delta T. We will put a dot over the Q to represent that this is an airflow rate and not a mass volume. A latent change is the process of adding or removing moisture without a change in the dry bulb temperature. As noted earlier, a latent change results in a change in the specific enthalpy, but not a change in the dry bulb temperature. The rate of water that is added or removed during humidification or dehumidification is shown in the equation M sub W, mass flow rate of water, is equal to the mass of the air sample times the change in humidity ratio. On the psychrometric chart, latent change is shown as a vertical line along some dry bulb temperature. As discussed earlier, latent change for moist air results in a change in the enthalpy of the air. In the dehumidification process, heat is removed from the air in order to condense out the water vapor. This can be shown on the psychrometric chart by observing the change in enthalpy during the dehumidification process. The rate of heat removal can be expressed using the enthalpy equation, and as shown, Q sub L is equal to the mass flow rate of the air times the change in enthalpy, which is represented as H2 minus H1. Please note that in these equations, M sub A, and often with a dot over it to represent flow rate, is the mass flow rate of air in pounds per hour. and the change in latent heat will be in BTUs per hour. Enthalpy is represented in BTUs per pound. It is very common in air conditioning systems for the air to undergo both sensible and latent change. These processes may occur separately or simultaneously, but in either case, the analysis used both the sensible and latent heat equations. The total heat removed or added is the sum of the latent change and the sensible change. This can be demonstrated on the psychrometric chart. Dehumidification and sensible cooling occur frequently in air conditioning systems. Air that passes over a cooling coil will often cool to the point that water vapor condenses out, so that the air is both cooled and dehumidified. The sensible change is the horizontal line as shown here. The latent change is represented by a vertical line along the dry bulb temperature. The total change is the sum of the change in enthalpy of both the sensible and latent changes. Evaporative cooling is a process that is very special cooling and dehumidification process that deserves a detailed discussion in itself. Evaporative cooling occurs frequently in air conditioning systems. Two noted examples are cooling tower applications and evaporative cooler. In evaporative cooling, a noticeable change occurs in the airstream. The dry bulb temperature of the air decreases even though no external cooling source is used. Evaporative cooling is an adiabatic process, meaning it is a process in which there is no change in the total heat content. In addition, evaporative cooling is a constant enthalpy process. So if this is true, then how does the cooling effect occur? The cooling effect comes from the evaporation of the water into the airstream. Evaporation is a latent process that requires heat, which comes from the airstream. It is an adiabatic process because in this process there is an exchange of heat within the air mixture. The sensible heat decrease is the same as the increase in latent heat, and the net effect is that there is no heat added or removed from the airstream. In addition, it is observed that the wet bulb temperature of the airstream does not change during this process. Evaporative cooling is only practical for air conditioning in very dry climates. In looking at the psychrometric chart, for a typical summer outdoor design conditions in a humid climate of, say, 90 degrees dry bulb and 74 degrees wet bulb, for example, evaporative cooling can only result in air cooled to 74 degrees dry bulb. Please note, evaporative cooling follows the line of constant wet bulb as shown here. However, if we started with air at, say, 94 degrees dry bulb and 10% relative humidity, which we might see occur in a warm, dry climate, evaporative cooling could produce supply air at 62 degrees Fahrenheit, which would be sufficient for cooling applications for comfort. Evaporative cooling also occurs in a cooling tower, but in this application, the process is to cool the water. Water is sprayed into an airstream, and some of this water evaporates. The heat required to evaporate the water comes from the airstream and also from the water that does not evaporate. The cooled water is then returned to the system where it can be reused. This is the end of this tutorial, Lesson 2.2. In Lesson 2.3, there are example calculations on using the equations and processes discussed here.